we will continue our discussion on pumping system design. So, as we have discussed that there are several aspects which a pumping system designer should take into account while he or she is designing a system. So, again I am writing pumping system design is very important, pumping system design. So, as I said that whenever someone pump design and pumping system design, these two are not same. So, whoever is designing a pump, he or she should know the requirement from the system engineer that what should be the head and discharge. Based on that, he will decide what will be the blade angle at the inlet outlet, what will be the impeller diameter, whether he or she will be using what kind of casing. Those things will be based on the input from the system designer. So, while we are talking about pumping system design, because we are not going to discuss about pump design. So, pumping system design, there are two important quantities which are very important, I mean to the system designer, that is total flow rate that we expect from a pumping system, total flow rate cube, and as I said that this is very much process specific because it varies from process to process. If we talk about a pumping system, rather if we think about designing a pumping system for power plant industry, we might require different quantities of water. On the other hand, if we think about designing a pumping system for let us say cement industry or any other industries, then their requirement of water may varies. So, depending upon the process, someone should calculate what should be the total flow rate that we need from the pumping system. Rather, the pump should deliver this amount of water to different points, that is different issue altogether. So, this is the total volume flow rate, that is very important and that is very much process specific, and system designer should know this information from the process people. So, this is process specific requirement as I said. And another important quantity is the total head that pump needs to develop. So, total head H that pump or pumps needs to develop. Pumps needs to develop. So, this is the quantity a system designer should calculate, because depending upon the level of pump house level where pump house is situated or located, and the other places where you need to supply water, their location, we need to calculate what should be the static height as well as, and to deliver water at those desired points, how much pipe, rather how long pipe we require, and what are the bends, I mean whether we need to insert 45-degree bends, 90-degree bends, and how much fittings will be required. Based on that, the system designer should calculate what will be the total head that the pump needs to develop. So, this essentially a system designer should calculate this one. How? Because this is having two parts, as I have discussed many a times, that it is having, one is static height, that is H static, plus another is dynamic head, that varies as K into Q square, where K is loss coefficient of flow. This is loss coefficient for flow. So, the total head that should be developed by the pump is having two components, one is static height, another is dynamic head. Static height is fixed because that is what I was discussing, that knowing the location or level of pump house as well as the distribution of water, I mean places where we need to distribute water, their location, if we calculate the difference of the height between these two locations will give you the static height. On the other hand, the dynamic head will essentially depends upon the frictional losses and losses due to presence of bends, valves, because many a times we need to put valve for controlling the flow. So, and this is very common. So, the presence of valve also will impart some amount of loss, rather that we need to take into account while we are calculating the total head loss. So, knowing these two quantities, total flow rate and total head, a system designer now should select that what kind of pump should be suitable for this operation. And in the very beginning I discussed that you know that if we require low to moderate discharge against moderate to high head, then of course we need to go for radial flow pump. That is what I have discussed, and this is very much suitable for domestic purposes, or sometimes in industries these pumps are used. On the other hand, if we require high discharge, that is high cube against so this is cube, this is H against a very low head H, then designers should consider axial flow pump. Sometimes again we need to go for positive displacement pump, that we will discuss in detail about their operational principle and constructional features. So, PD pump, or sometimes they are known as PD pump or positive displacement pump. See, these positive displacement pumps normally they are used for developing very high head against a constant flow rate. This is very important, because positive displacement pump will deliver high head, but the flow rate will remain constant. So, if that is the case, then we have to go for positive displacement pump. So, depending upon the requirement of the process and depending upon the layout, I mean a process layout, that means where we need to supply water and their level difference, also pipeline routing, I mean where we can place, how we can place pipes, valves, fittings to supply water at different locations. Based on that, designer should calculate the total head requirement, and process itself will dictate the how much amount of water we need to supply from the pumping system. Knowing these two quantities, system designer should select what kind of pump is suitable for that particular case. Now, this is the several aspect. Now, how someone will calculate the total head, that is very important. So, this is very important in a sense that the practicing engineer and design engineer, it is not always possible to follow that fluid mechanics. So, while you are calculating the total head, this is very important. As I said, I am not going to talk about total flow rate, because this is very much process specific requirement. So, that will be dictated by the process people. So, total head, while you are calculating total head, this total head is having two components. As I said, one is static height, that is also fixed, because we have nothing to do, it depends upon the layout, I mean where the pump house should be located and the desert points where we need to supply water. So, the height difference between these two locations, or rather the locational difference between the height of the different locations will give rise to the static head, that is also fixed. But what is very important is the dynamic head, and that essentially depends upon the frictional losses while fluid is flowing through the pipe, then losses in presence of valves, vanes, fittings, etc. So, this is normally we call it minor losses, and also this is very important, because sometimes we need to put flow meter, to calculate whether how much quantity of water being discharged by the pump, and that flow meter essentially will provide some resistance to the flow, and and for that, to overcome that resistance, again we need to have some amount of head from the pump. So, this flow meter also provides some resistance, to the flow, and for that we need to know that So, this dynamic head loss while you are calculating, we need to consider these three aspects. So, knowing these three aspects, how we will calculate frictional losses in pipes? As I said you, frictional losses is calculated based on Darcy-Weisbach equation for flow through a pipe. So, that is essentially give HF is equal to FL by D V square by 2G. Now, L is the length of the pipe. If we know the diameter of the pipe D and F is the friction factor, while V is the recommended velocity through the pipe. Normally, from my experience, although I have worked over a very small period, the recommended speed of water, rather the flow velocity through the pipe is normally 1.5 to 2.5 meter per second, and this is dictated by several reasons, because it should not erode the pipe material. So, depending upon this, and also we need to provide some support, because when water is flowing through the pipe, then we need to provide some support from the ground to keep or to hold the pipe in place. So, that is why this is the recommended velocity. So, based on this velocity, I mean we need to know what is the Reynolds number, because we know if it is laminar, then we can calculate 64 by RE, or it is always highly turbulent. So, we need to calculate that from the Moody's diagram. So, normally this friction factor is calculated from the Moody's diagram, because a pipe, it is very difficult to have a smooth pipe. So, we should have roughness. So, knowing the roughness and the Reynolds number, we can calculate friction factor from Moody's diagram. But it is what is we need normally calculate from fluid mechanics, but the practicing engineer or design engineer, normally they do not go for calculating this frictional head loss using Darcy-Weisbach equation. I mean, they calculate using this equation, but they are having their own handbook. From there they calculate that if recommended speed is like this, then if the diameter of the pipe is this, then what should be the head loss per 100 meter if the flow velocity is this. So, there are some handbook, from there they calculate, but essentially that handbook is prepared, or the data tabulated on this handbook are based on this equation. So, in using this we calculate the frictional head loss. So, the frictional head loss is calculated whether we are going to calculate using our this Darcy equation, or sometimes if we follow the pumping system design handbook, that that losses is ready made available, because if I know the recommended speed and if I know the diameter, then for 100 meter length what should be the frictional head loss, that we calculate using that book. So, this we obtain from frictional head loss. Now, what about the minor losses? Again, minor losses, if you would like to consider that because of the presence of valves, bends, bends might be 45 degree, 90 degree, and it may be again 60 degree. So, depending upon the bends and also the valves, and also there will be some fittings, some kind of convergent portion, there will be some divergent portion. So, there will be some losses. So, again if we look at our basic fluid mechanics, that flow through a convergent section, divergent section, we need to calculate the losses. So, this normally it is advisable to calculate exact losses using those formula that is there in fluid mechanics book, but sometimes these minor losses are taken, because minor losses are taken 50% of the total head loss. So, minor losses are taken 15% of the total loss, and this is not very bad assumptions, because sometimes if we take minor losses at 15% of the total head loss, if question is considering 15% of the total head loss to be the minor losses. Now, if we design the pumping system and if it so happens that our calculation is underestimating the head loss, then pumping operation will have trouble. But it is seen that normally 15% consideration of 15% of the total loss to be the minor losses, and that is quite comfortable to the pumping system design. So, that is why, and that is taken from wide experience of the system designer. So, minor losses are taken of the 15% of the total losses, total loss. And flow meter, whenever flow meter is there sometimes, and we need to calculate what is the loss. So, again we need to calculate that and whenever we are purchasing or procuring flow meter, loss coefficient will be there, and if we know the velocity, then from there we can calculate the total loss. So, knowing all these losses and static height, someone has to calculate total head being developed by the pump. So, this is one aspect. Now, I will discuss one another important aspect is that sometimes this is very important aspect I will discuss, that it is always recommended in a pumping system that suppose our requirement in a particular process, if requirement is cube meter cube per second, and head is H meter. So, if this is our requirement from a pumping system, and say a particular pump can deliver cu meter cube per second against a head of H. So, only one pump should be installed in the pumping house, it is not recommended. So, while you are talking about a pumping system, a good designer pumping system, a good designer always tries to put at least 2 or 3 pumps. One should remain as a standby mode, because if you have only one pump may start malfunctioning because of so many other reasons. So, if one pump start malfunctioning, then it will be interrupted, water supply should be interrupted, and that if it is interrupted, there are industries it will create, that interruption of the water supply will lead to a severe damage. So, to save the entire system, at least a designer should consider that there will be at least one standby pump to prevent the total system. So, while we are talking about pumping system design, maybe we are taking water from a sham, maybe if it is a sham. So, and we will have at least 2 pumps, to supply water, and all of them will supply water to a common header, and that is a common header. So, this is known as common header, and from common header the branch line should be connected to different places where you need water. Now, so fine, so this is let us say pump 1 P1 and this is pump 2 P2. So, while they are drawing water from a reservoir sum, and I have discussed that normally it is always advisable to have a design of pumping system, rather pumps should be allowed to run under flooded suction mode. So, pumps should be allowed to run, under flooded suction mode. What is flooded suction mode? That is, the impeller axis should always be below the water level, so that the if we have a negative suction mode, then it might happen that we need to sometimes remove air, or if by doing some priming operation. So, it is recommended that it will have a flooded suction mode. So, now normal practice is that these pumps should run, but pumps should be driven by electric motor. So, again as designer, another aspect of pumping system, a good pumping system design is to that, okay fine, we have 2 pumps, maybe one is standby, one is operating, and we may have interchangeability, flexibility, so that we can have after running a certain hours of one pump, we can allow the pump to be under rest, and then we can operate another pump, only to have a continuous supply of the water. Now, again it is advisable that, because when you are running pump using electric motor, so because of sudden stop of electricity supply, although we are having 2 pumps, but because of stop of electricity supply, we cannot supply water to the desired points. So, again our designer should look into this aspect, and that is why again another pump, the pump of same capacity or same head should be there in the system, and that pump should run using diesel engine. So, this pump again, and it will also be connected to the common header. So, this pump, let us say P3. So, now P1 and P2, maybe these are the electrically operated pump, while P3 is the pump which is operated by diesel engine. So, this is diesel engine operated pump. Why? Because as I said you, because of sudden stop of supply of electricity, both the pumps, although they are capable of supplying water, there are no problem from the pump side, but still because of stop of supply of electricity, pump may stop, and we may have disturbances in the water supply. So, that should not be the case. So, that is why we need to again put another pump that should be operated by diesel engine, and that is in emergency. So, this is known as sum. So, this is sum, from where we have connected these 3 pumps, and all of them are supplying water to a common header, and from the common header again there will be a few branch lines. From there water should be distributed in different points. I would like to now discuss another important point that needs a few analytical methodology. Suppose let me discuss about the problem. So, suppose fine, these 3 pumps are there and these 3 pumps are identical pump, and maybe one pump can only running by one pump we can supply the desired amount of water to the different points. So that is fine. So we have 2 different another pumps that will remain as a standby mode. Sometimes we need to have flexibility because of, as I said you, because one pump may start malfunctioning, and also it is advisable to give at least a few time that is called rest that pump, otherwise pump may start malfunctioning. And another pump that is operated by diesel engine should be there only to take into account that sometimes it may happen that electricity should not be there. So this is the overall situation. Now my question is, these 3 pumps have been installed in a pump house. So whenever a system is designed, and it is designed keeping in mind that there should be provision of installing another pump in future if system demands more amount of water to be supplied from the pumping system. Probably I have discussed in one of my lectures that never industry people will want that we should have another new pump house, because installing new pump house, rather construction of new pump house is of course very costly. We need to have at a time cost, and on the other hand, if we have another pump house, then again we need to employ another operator to look after that pumping operation, and that for that again that will lead to another cost. So considering these aspects, whenever a pumping system designer is designing a pumping system, he or she should keep in mind that provision should be there to install a few more pumps in future if system demands more amount of water, or either install more amount of water, or sometimes it might so happens that okay, the head that is being developed by the present pump or existing pumps is not sufficient to cater water in a place, or newly installed some equipments. So we have to have provide higher head. So now question is, whenever it is normally seen that normally head developed by a pumps. So suppose all these 3 pumps are identical pumps, so they are providing that their HQ characteristics are same. Now depending upon the system resistance, they will fix up their operating point and we will get the desired head and discharge. Now it might so happens that the system requirement is now, instead of Q, it is Q1 Q plus something else. So now present system requirement is, so if because of some installation of new plant or new equipments, the present system requirement, if present system requirement is Q plus let us say Q1, and this Q plus Q1 amount cannot be supplied even by operating 2 identical pumps in parallel. So this situation might happen that to meet the present system requirement, because of installation of a new plant or new equipment, the system requirement is Q plus Q1, which is of course greater than Q, and this amount is such that it is not possible to supply from the existing pump even by running 2 pumps in a parallel mode. So then again we have to have another pump, to meet that shortfall of water. So while we are connecting another pump in parallel with the existing pump, that means this amount is such that even if I run these 2 pumps in parallel mode, we are not in a position to meet the demand. That means again we need to install another pump, and that pump should run in parallel with the existing 2 pumps. So in that case, we have to now fix up what should be the head and what should be the discharge that we are looking for the new pump. Not only that, the newly installed plant or newly installed equipment, that may not be in the exact that may not have the same resistance with the with the previous system resistance. So after installing new equipment or new plant, the system resistance might differ, and as I told, I do not know that whether I told you or not that pumping system, whenever we are connecting pumps in parallel, they will try to always follow the least resistance of the system. So maybe you are installing a new pump that should be connected in parallel with the parallel operation of another 2 pumps, but if the resistance of that system is even much higher than the previous system resistance, then that pump may start malfunctioning, rather pump tripping may occur. So if this kind of situation occurred, then how we can get rid of this problem, that I will discuss by taking an analytical methodology. And today I stop here, and I will probably continue this kind of analytical methodology, how we can get rid of this problem by doing a very simple methodology, and that should a pumping system designer should know as a remedy. So we will discuss that aspect in my next lecture. Thank you.